Hi students, let us discuss some property of number systems. So we make use of numbers in our day-to-day life in many different aspects. For example, while you are counting some money, you make use of numbers. While you are doing measurements of certain things, maybe your body weight or some area, so you again make use of numbers. There are n number of applications we make use of numbers to quantify certain things. So let us say I have certain number called n. This number n is always associated with something known as radix or base. Sometime we make use of notation r, sometime we make use of notation b. So this is known as the radix. So what are the property of this radix? Let us have a discussions. Remember, this base or radix r is always a positive real integer. It is always a positive real integer. In other words, r cannot be a negative number like -4. R cannot be something like a fraction quantity, let's say 7.67 or something like that. Or R cannot be like a complex number, let's say 3 plus j4 or something like that. So these are not valid values of R. Okay, R is always a positive real integer. Secondly, generally, okay, R value it starts with 2 onwards. Although it can be argued why the R cannot be 0 or 1, I'll come to the reason of that after some time. But generally, in most of the practical cases, the minimum value of radix or base is always at least 2. So depending on this radix value, we have different number systems. So whenever the R value is 8, we say it is octal number system. Whenever R value is 16, we say it is hexadecimal number system. Whenever R value is 10, we say it is decimal number system. Whenever R value is 2, we say this is binary number system. So these are 4 popular number system we generally make use in our particular course. So here one more important fact that you should know, student, is suppose somebody is saying that my number n having base r, remember that this number can contain the digit up to r minus 1. So this number n is comprising of so many digits, and if I am saying that the base is r, then it means that these numbers that it will contain is 0, 1, 2 like this up to r minus 1. The maximum digit that is allowed is r minus 1. That's why in a octal number system, because I am using the base 8, so we make use of the digits up to 7. So 7 is the highest digit, which is r minus 1, which is 8 minus 1 in this case. In the hexadecimal number system, so because the r value is 16, so highest digit that is we make use is f. F stands for 15. In the hexadecimal number systems, 0 to 9 fine. Then for 10 we make use of A, for 11 V, for 12 C, for 13 D, 14 E, and for 15 it is F. Okay, so if it is 16, so maximum digit is 15, so 15 is meant for alphabet F. In decimal number system, because base is 10, we make up to 9. In binary number system, because base is 2, we make use of 0 and 1. Similarly, if I say it is base 5, we can go up to 4. For example, friends, suppose if I write a number, let's say I'm writing 234.56 and I'm writing the base is 5, this is a invalid representations because you are already using the value 6. Then how the base can be 5? If I ask you what could be the right value of this base, you should say because the highest digit which is used in this particular number is 6. So if the highest digit is 6, then base should be at least 7. Because if the base will be 7, then it can contain up to 7 minus 1, 6. So the minimum value of base that you can make use in this particular number system is 7. Okay. Now, let us solve one question, students. Okay. So this question is asked in one of the engineering service papers, old papers. So the question is, what is the minimum possible value of base b in this number? Okay. So the number is 23a, then point BC4, base is b. What is the minimum possible value of b? Okay, when I ask this question generally in the class, so many students they reply like the answer is 16 because in the popular number systems, the alphabets A, B, C, D, E, F, they are used in hexadecimal number system, and because A, B, C are used, so it is representing hexadecimal number system. Okay, but is that the case? That's not the right way actually, right? So let us see what it will be. So because the maximum digit that we are using in this case is how much? A is 10, B is 11, C is 12. So because up to 12 it is used, so the value of base it can be greater than equals to 13. Because up to 12 it is used, so any value beyond 13 if you take it is absolutely fine. So the minimum value if they ask you, the answer will be 13 in this case. Minimum value will be 13. So here I am writing here greater than equals to 16 is also possible. 16 is one of the answer, but if somebody asks you with a minimum answer, then it should be definitely 13. I hope this logic is clear, student, right? So whatever I said, so you can make a note of it. R is always a real positive integer, and generally its value is greater than equals to 2. Okay, and if a number is radix is r, then it can use up to the numbers 0, 1, 2 up to r minus 1. Any number as system associated with some base or radix, if a radix of a number system is r, it means the corresponding number system comprises of r number of distinct symbol, or it will contain the digits 0, 1, 2 up to r minus 1. Now, students, what is the problem if I take the value of r as 1 or 0? Suppose you say that you have a number called n and its base is 1. If base is 1, what are the number it can contain? It can contain up to b minus 1. So b is 1, it can contain up to 0. So if the base is 1, then it will contain the numbers only 0. So I mean, if the base is 1, you cannot have anything else other than these zeros. But what is the purpose of number? To quantify some things. So here, if you are using the base as 1, you are not able to generate different numbers. It is giving only one pattern. So which is not the purpose of a number. So let's say if you are using a 2-digit number or a 3-digit number, you want, like this pattern should change. If it is only like this, it is meaningless. That's why you can make arguments that r is one of the valid way, but it is actually meaningless. That's why I said in practically, generally we take the minimum value of r as 2. So what is the problem if the base is 0? If the base is 0, then what it will contain? It cannot contain any digits. Don't say that minus 1, minus 2 like that. No, those are not valid. So that's why base 0 and base 1 are excluded. So we start with 2 onwards. I hope this is clear, students, and these points we'll be using after some times to solve some questions, logical questions, which are asked in the previous year gate papers. All right. So having said this property of number, now let us see to one more important category from where questions are coming not very frequently, but yes, sometimes questions are being asked in the previous year gate papers, and that is nothing but the number system conversions. So what is the need of number system conversion is why you should study number system conversion? One of the by default answer is it is important from gate point of view. Of course, that's why we are studying this. Secondly, students, what is the purpose of number system conversion is? So it may happen like you have a number in base 6, let's say, you want to know what is this numbers look like in some other base, might be base 8. Or you have some number in one base, you want to know what this quantity in some other base. In such kind of cases, the knowledge of number system conversion is quite essential. So I have classified this number system conversion into 5 categories. So the category 1 is base x to base 10. Category 2 is base 10 to base x. Category 3 is base x to base y. Category 4 is base 2 to base 8 and vice versa. Category 5 is base 2 to base 16 and vice versa. Okay, so if you know these 5 conversion techniques or this particular 5 models, then any question related to number system conversion you can easily answer. Okay, so so this is basically, students, a method oriented or a process oriented problems. Okay, so here no need to elaborate so much things in the theory. So that's why I have just taken certain examples, so that through these examples I can give you a clear idea like how to convert a numbers from one base to other base. So first category, student, is base x to base 10. Okay, so you have certain numbers. Okay, this number in some other base, like in this case it is in base 16. I want to know what will be its equivalent numbers in base 10. Okay, so remember, students, whenever you have this base x to base 10, so you just remember one simple keywords. So this kind of problem can be solved using polynomial expansion. Polynomial expansion. So you just remember this term, polynomial expansion. Okay. So here what I'll be doing is, so this number which is AF3.15, this is in base 16. I want to know what is its equivalent decimal. So what I'll be doing is, I'll be expanding this particular numbers in a polynomial format by taking this radix. The radix is 16, so I'll be expanding this with respect to the 16. So you take this as the reference point, then here it is 16 power 0, 16 power 1, 16 power 2. So A is nothing but 10, in hexadecimal number it is 10. So 10 into 16 square plus F is nothing but 15, so it is 15 into 16 power 1 plus 3 into 16 power 0 plus 1 into 16 power minus 1 plus 5 into 16 power minus 2, right? So this is the reference point towards this increasing power of 16, towards this decreasing power of 16. So here 16 power 0, 16 power 1, 16 power 2, 16 power minus 1, 16 power minus 2. So these things I have multiplied. Take a calculator and solve it, friends, and if you solve it, the answer what you're supposed to get is 2860.082031225. So for better accuracy, I have evaluated this for like 7 to 8 places after the decimal points, but you may use up to 2 to 3 as per your choice. So this is its base 10 equivalent. So any number, if it is in some arbitrary base, you want to convert this into decimal. So you simply expand that its corresponding polynomial. So I think, so having understood this, so you don't have any issue to answer the next questions. That is, I have a number in binary. I want to convert this into base 10. So how will be doing in this case then? So the number is given as 1011.011 and this base is 2. So you want to expand this in the polynomial form because you need the decimal equivalents. So again the same story. So this is your reference point. So towards this increasing power of 2, towards the decreasing power of 2 because the base is 2. So that's why 1 into 2 power how much? 0, 1, 2, 3. 3 plus 0 into 2 square plus 1 into 2 power 1 plus 1 into 2 power 0 plus 0 into 2 power minus 1 plus 1 into 2 power minus 2 plus 1 into 2 power minus 3. Okay. Take a calcium and simplify this, students. If you do this, the answer what you're supposed to get is 11.375. So this is what is your category 1, like how to convert a base x number system to base 10 number system. And the key word is polynomial expansion. You remember this. The second category is base 10 to base x. So you have a number in decimal number system. You want its corresponding some arbitrary base. What is the number? Like base 10 to base 8, base 10 to base 6, something like that. So here, in such kind of, what is the keyword you should remember is, we handle this problem in two parts. Okay. So we have something known as the integer part. So integer part, students, to the integer part what we do is, we make use of repeated division. I'll explain it what it means. And the fractional part, we always make use of repeated multiplication. What is the meaning of this? So let us understand by taking this example, then we'll get the clarity. What is the meaning of this repeated division and these all things I'm saying. Okay. So you need to solve this problem. Okay. So student, what I'll be doing in this case is, so I'll be dealing this integer part separately and the fractional part separately. So here the integer part is 234. So I'm taking here 234. So what you do is you keep on dividing these numbers by this required base. The required base is 8. So you keep on dividing these numbers by 8, repeated division. So 8, if you do it, 8 2 just 16, then you have 7 4 8 9 just 72, and you are left with 2. And then you have 8 3s are 24, and this is 5. And again, if you try, then this is 0, and this is your 3. So that's all. You keep on doing this unless until you're getting 0. And while dealing with the final answer, you give the answer from the bottom to top approach. In other words, this 234, if I ask you what is the octal equivalent of it, then the answer is 352. Because this way, if I move, 0 is anyway, it doesn't matter. 352 in this sequence I have written. So I have handled the integer part this way. Now this is the time to deal the fractional part. So this fractional part is a bit tricky, students. Listen carefully. Only one time if you understand. So there won't be any other confusion then again. So for the fractional part, what I'll be doing is, so this number 0.1285. So this is the number, right? In the fractional part, I mean these segments. So here you continuously have to multiply this by 8. But here one point I will be telling you, you listen first. So first you multiply, so this number into 8. If you do that, you take a calci, then you will get this is 1.0280. 1.0280. But while then again you have to multiply by 8. But before you multiply this, students, you make sure that the integer part of this number is always 0. In other words, like here the integer part is 1. So even though it is 1, you simply discard it, you take it as 0, and you bring this 1 here. So while giving the answer, like here I have given this way, so I'll be using these numbers to give the answer. So although I got 1, so I'll be taking it 0. So this one I have written here. Then again multiply by 8. If you multiply by 8, so 0.0280 into 8 if you do, you get this is 0.2240. So what is the integer part here? 0. So from every iteration, I have to get one number. So if it is anything other than 0, you take it out. If it is 0, you take this 0 as it is. Then again you multiply this by 8. If you multiply this by 8, so this is coming as you take a calci. So 0.792, sorry, 0.2240 into 8. If you do it, it is coming as 1.7920. 1.7920. As I said, in every iteration, we will be getting a number. So this one I'm writing here. So you take this as 0. Then again you multiply by 8. If you multiply by 8, so you get this is 6.3360. So again the integer part is 6. So from every iteration you have to get one integer, right? So this 6 you write here. So this 6 you write here, and you take this is 0. You again multiply by 8. Then if you are again multiplying by 8, you get this is 2.6880. So this 2 you write here, again you make it 0, again multiply by 8, and this process will continue. So in the GATE exams, so they will be asking you up to 2, after the radix point of two numbers or 3 numbers, like that they will ask you. But while giving the answer of the students, so what we'll be doing is, we'll be giving the answer in the top to bottom approach. For example, so like here it is known as bottom to top approach. This is the top to bottom approach. So how will be giving this? So this is these numbers 0, 1, 6, 2, like that. So 1, 0, 1, 6, 2, like this. So this is basis 8. So 234 is equivalent to 352, and 1285 is equivalent to this 10162. So this is how you have to deal with. So that's why, students, whenever I think many of you might have seen, like while converting a numbers from base 10 to base 2, let's say you have a number 53.75. So this is the number in base 10. You want to know what is its base 2 equivalent. So what we do then, we repeatedly divide this 53 by 2, and we continuously multiply this 0.75 by 2. And this process you have to continue. So the fractional part might be odd to some of you. So if I am continuing for this, let's say, 0.75 into 2, this would be 1.50. So this one, you take it out, you make it 0. You multiply by 2. So it is 1.00. You take it as 1 and then it's 0. So now it is 0.00. So it is ending here. So sometime it is a non-ending series like this. Sometime if you get 0.00, so it's an ending series. In this case, you may do for 53, then point, then in place of 75, you can write the answer as 1, 1. You can write the answer as 1, 1. Okay, student, here let's say in this case, student, this is the not the exact answer because I didn't get here 0.00 like this. So that's why it's a non-ending series. You can put some dots like this. So always remember, student, this is one point. It is always possible to get the exact equivalent of an integer part, but it may not be always possible to get the exact equivalent of a fractional part. Because in the fractional part, you don't get 0.00, it is a non-ending series. Yes or no? So that's why in one of the computer science problem, one question was asked, a number given 0.15, what is the, like if this number is in base 10, what is the binary equivalent? So what you'll be doing, you'll be multiplying this continuously by 2. 0.15 into 2 is 0.30, you got 0. Then you multiply it by 2, you get 0.60, you again got 0. You multiply by 2, you get 1.20, you take this is 1, you take this 0. So multiply by 2, you get 0.40. So you take 0. You multiply by 2, you get 0.80. You take 0. You multiply by 2, you get 1.60. You can take this 1 and this is 0. So like this you see, this is a non-ending series. If it is a non-ending series for this 0.15, you may say the answer is 0.001001 and so on and so forth. So this is a non-ending series because we are not going to get 0.00 anywhere by observing this pattern. So the exact binary equivalent of this number we cannot tell because this we are not getting 0.00. That's why it is very popularly said it is always possible to convert an integer part, but it may not be always possible to convert a fractional part. Okay, so I hope you understood like what is the meaning of this base 10 to base x integer part repeated division, fractional part repeated multiplication. In the fractional part, we are going from top to bottom, and here we are going from bottom to top. In the integer part, we are going from bottom to top. Let us see the third category, that is base x to base y conversions. So here I have taken one question, students, like 18.6 in base 9 is how much in base 11? So the previous two category was base x to base 10 and base 10 to base x, but here it is from any base to any other base. So what is the process that it has to be followed in such kind of cases? You make use of base 10 as a intermediate number system. So because we know how to convert a number into base 10 or how to convert a number to other number from base 10. So if you make a base 10 as an intermediate number system, you can solve this problem. So for example, like here I have taken how much is this 18.6 in base 9 is in base 11. So to solve this problem, so the question is 18.6 in base 9 is how much in base 11, right? 18.6. So here the first step is I want to know how much is 18.6 in base 9 in base 10 format. How much is it? So how to convert any number system into a decimal number system? The technique is the polynomial expansion. Any number to base 10 is polynomial expansion. So this is 1 into 9 power 1 plus 8 into 9 power 0 plus 6 into 9 power minus 1, right? You simplify this. If you simplify this, the answer what you're getting is 17.666. 17.666 like this. So this is the answer, 17.666. Okay, so now the next step is, so this is your step 1 and this step 2 will be this 17.666. Okay, this in base 10 is how much in base 11. So that's why, so it's like I'm converting now base 10 to base 11. So you have to go by that integer part separate, fractional part separate. So 17 the integer part. So I'll be dividing this with 11. So it is 1 and this is 6. And again, if you do with 11, then this is 0 and this is your 1. So I'll be giving the answer from bottom to top. So it is 1, 6. So 17 in base 10 is equivalent to 1, 6 in base 11. Now the next thing is this 0.666. What we'll be doing then in this case? We'll be multiplying this with 11, repeated multiplication by 11. So 0.666 multiplied by 11. So if you do it, you get this is 7.326. As I said, so you have to take this 7 and this you make it 0. Now you again multiply with 11. If you multiply with 11, so 11 into 0.326. So this is coming as 3.586. So this 3 is coming here. So this is your 0. Then again you multiply this with 11. So 11 into 0.586 if you do. So this is coming as 6.446. So this 6 you'll be bringing here and you make it 0. You again multiply by 11 and this process will continue. But while giving the answer of this, so you have to go from top to bottom. So for 17 it is 1, 6 and for this 0.666, so this is also, it looks like a non-ending series. This is 7, 3, 6 and dot 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 something like this. So this answer is 18.6 in base 9 is equivalent to 16.736 dot 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 in base 11. So I believe if you get any questions of this category, so you can easily answer this. Okay, now let us see the next category, which is your base 2 to base 8 and vice versa, similarly base 2 to base 16. In fact, these things friends, these two comes in kind of a similar category, but anyway, let us see them one by one. So first, let us see this category, that is base 2 to base 8. Okay. So for that, so what I am doing is, so I have again taken two questions. One question is how to convert base 2 to base 8 and next question is how to convert base 8 to base 2. Student, here actually there is a pattern called like if you can express the required base like given base to the power integer, we have something like here you have base 2, you want to get its base 8 equivalent. So this 8 is nothing but 2 power 3. 8 is nothing but 2 power 3. So you are getting this number 3, right? So whenever you get something like this, the required base is 8, given base is 2. So required base is given base to the power integer. So the integer is 3. So you make the grouping of 3 digits. I believe many of you know how to convert this base 2 to base 8. You always do the grouping of 3. But from where that 3 comes? The 3 come from here. So let's say then why in the binary to hexadecimal we do the grouping of 4? Because there 16 equals to 2 power 4. You got 4. That's why you do the grouping of 4. So here what is the process? I'll be doing the grouping of 3 binary digits and we'll be writing its corresponding equivalent base 8 number, right? So again your reference point is this point is the reference point. You do the grouping of 3. So this is a grouping of 3, then this is a group of 3, then this is a group of 3. Similarly, this is a group of 3 and this is a group of 3. In case if there would have been some deficit, you can put zeros. Then you find the octal equivalent of each of these groups. The octal equivalent of this is 101 is 5, 110 is 6, 101 is 5, 011 is 3, 110 is 6. So the answer is 565.36. So this is in base 8. In fact, you might be wondering like, sir, how you are finding the octal equivalent of this. So these are the decimal equivalent. In fact, you can try this out. If you have a single digit, so let's say if I have a number 7, 7 in base 8 is equivalent to 7 in base 9 is equivalent to 7 in base 10. In other words, if you have a single digit, so its base, if you keep on increasing, it will still remain the same. Because equivalently, if you find its corresponding decimal, it will be always 7, like if you see it, so what is the decimal equivalent of it? So 7 into 8 power 0. Here it is 7 into 9 power 0. So something power 0 is always 1. So it doesn't matter actually. So whether you find the decimal equivalent of this or the octal equivalent of this, meaning is same, because decimal equivalent is how much? 5. So the octal equivalent will also again 5. But in a very specific way, you should say it is octal because this is a base 8. So similarly, while dealing with this base 2 to base 16, okay, we can again solve this problem this way. So here base 16 is nothing but 2 power 4. So you have to do the grouping of 4. So again you take this point is the reference and do the grouping of 4. So group of 4 and group of 4. Similarly, group of 4 and group of 4. So 1101, 8, 4, 1, 1101 is 13. 13 is how much? C. C is 12, right? D. So this is D. 1001 is 9. This is 1010 is A, 10. This is 5. This is 15 is F. And this is 5. So this answer is D9A5, D9A5, F5. This is in base 16. Where is the dot? D9A. So dot is here. This is the answer. So in the reverse way, how will be proceeding? Reverse way means if the number is in octal equivalent, so how to get its corresponding binary, right? So the process is exactly opposite, students, okay? So what you do is, so in this case, whenever you are supposed to find the octal equivalent, I mean octal is given, you want to find the, what is that? The binary equivalent. You replace each of this octal digit by its 3-digit binary equivalent. Okay, from where this 3 comes, again the same story, this number was 3. In this case, we will be replacing by 4-digit equivalent because this number is 4. So here each octal digit, I will be replacing it by its corresponding 3-digit binary equivalent. So 6 is 110, 7 is 111, 3 is, although 3 can be written as 11, but strictly it should be 3-digit. That's why you are not supposed to do the mistake by writing 11. You should write this is 011. Then dot, then you have this 2. 2, you can write this as 10, but you write this is 010. Then you have this 4. 4 means it is 100. So this is what is your base 2 equivalent. So this is the process. Similarly, in this case, students, you see the number is ABCD.5EF96. This is in hexadecimal notation. What is its base 2 equivalents? So in this case, again, because this is 16 is 2 power 4, I'll be replacing each of these hex digit by 4-digit binary equivalents. So what is A? So A is nothing but 10. So 10, how much is it in binary? A is 1010. Then you have B. B is 1011. Then you have C. C is 1100. Then you have D, 1101. Then you have dot, then 5. So 5 is 0101. Then you have E. Then you have E, 1110. Then you have F. F is 1111. Then you have 9. 9 is 1001. And then you have 6. So it is 0110. So this is the base 2 equivalents. So yes, this number is very large. That's why you are getting so many bits in this corresponding binary also. So I believe this is absolutely fine, right? How to convert base 2 to base 16, base 2 to base 8, and base 8 to base 2, and base 16 to base 2. So this is clear. So I hope, students, the number system conversion is clear to you. In the next video, we are going to see some interesting questions, and most of them are asked in the previous year GIT papers. So let us continue in the next video by questions discussions of whatever the concept we have learned so far.